My name's Omar, and this is Blaine, and we're reverse engineers on the FireEye Labs Advanced Reverse Engineering team. So we're going to be talking about finding evil in the Windows 10 Memory Manager today. So long story short, the Memory Manager has changed a lot between Windows 7 and 8, and then again even more between Windows 8 and Windows 10. We've gone ahead and done a whole bunch of research and then integrated it into both Volatility and Rekall, so you don't have to do that research. Okay, so who am I and why am I talking about the Windows 10 Memory Manager? So my name's Omar Sardar. I'm a staff reverse engineer on Flare. My job is to reverse engineer malware daily and to reverse engineer it accurately. On top of that, I also automate reverse engineering efforts. And one of my niche roles on the team is that I actually analyze Windows internals for FireEye product. Anytime a forensic artifact shifts in Windows, I usually dive in, figure out if the algorithm behind it has changed, I locate the object again, and then I propagate that back up to FireEye product so we have the latest detections. Now, I'm not 100% defined by my job, so outside of work, I enjoy biking, I make pizzas, and I drink espresso and beer. You can follow me on Twitter at osardar1.
Hello, everyone. I'm Blaine Stansel. I'm a reverse engineer on FireEye's Flare team. I reverse engineer malware, and I also support our Commando VM and Flare VM virtual machines. So Commando is our red teaming or penetration testing virtual machine, and Flare VM is our reverse engineering specific virtual machine. So who here, show of hands, has heard of the Flare On challenge? Okay, a few hands. So for those who don't know, the Flare On challenge is an annual reverse engineering competition put on by FireEye's Flare team. It's really hard, really fun. Completed 2 of them in the past, got some flair, and this year I'm really excited because I've actually authored a challenge. So when you do the challenges, keep a little lookout for that little red icon over there. Outside of work, I enjoy gardening, DIY projects, and of course, beer. You can find me on Twitter at malwaremechanic.
All right, thank you, Blaine. So why don't we rewind the clock a bit? Let's have a story time now. The year is 2016. I'm a senior reverse engineer, crushing malware on the team, writing up reports, closing out tickets, et cetera, et cetera, et cetera. I get a call from my manager, Josh Homan, and I can practically feel his hair on fire as he tells me about how we have customers running our Windows endpoint, and they're not able to actually extract memory, and they're not able to search for forensic artifacts that way. And as a backup, they tried Volatility, Rekall, Redline, Memorize, and they were all actually failing, so it wasn't just us. So it became my job to dig into Windows 10 and figure out what was actually going on. Now, they have a saying that when you're a hammer, everything looks like a nail. Well, when you're a reverse engineer, everything looks like it needs to get dropped into IDA Pro. So I dropped the kernel into IDA Pro and started reversing. This talk today is about some of that effort, some of the findings that were done, that were made, and then the second half of the talk will be how we integrated that into Volatility and Rekall, so you don't have to drag it into IDA Pro and spend months of your life on it. Okay, so I'm going to start this off by going through a quick Memory Manager crash course. I'll talk about how the Memory Manager's changed a little bit between Windows 7 and 8, and then 8 and 10. I'll cover some of the updates, but the biggest update, I think, as most of us know, is the introduction of compressed memory. So I'll discuss how we can go about accessing that compressed memory, and then I'll hand it off to Blaine. Blaine will take over and discuss the creation of Volatility and Rekall plugins. And finally, he'll go over a malware sample I reverse engineered about 2 months ago. So it's a pretty real sample. And we'll do a before and after comparison with Volatility, and we'll cover what we didn't see before now and what we see now with the Flare research integration. Okay, so let's get started with the Memory Manager. Now, in Windows, anytime you fire up a process, whether it's Calculator, Notepad, or omar.exe, that process gets 2 gigabytes to 128 terabytes of memory. So that's actually what we call virtual memory, and it's the Memory Manager's job to go ahead and get that virtual memory and then translate it to physical memory. Physical memory is memory that's located on the sticks of RAM within our laptop. The Memory Manager also takes care of moving data back and forth between the hard drive. That's an operation that we call paging. In paging is when you bring memory back in from the hard drive into RAM, Outpaging is the opposite. Now, on top of that, the memory manager does a whole bunch of other things, and a lot of them revolve around performance optimization. To back that performance optimization, a whole lot of bookkeeping is done. This is like a very serious understatement here. So I just covered virtual memory really briefly. Now, let's say omar.exe is a 64-bit process on Windows 10. I'm going to get 8 terabytes of memory to work with from the kernel. Now, I don't know about you guys, but my laptop does not have 8 terabytes of memory, let alone 8 terabytes of memory for each process that I'm running. It's the memory manager's job to provide each process with the illusion of having 8 terabytes of memory to work with. And it does all sorts of tricks to make that illusion work. That 8 terabytes of memory space is what we call virtual memory. If you want to reach data within your swath of virtual memory, you need to have an address that you want to read data from. When you read data from an address, you get it back in page granularity. And a page is just hex 1000 bytes of data, or 4096 bytes of data. The actual location of the data is transparent. omar.exe or notepad.exe does not care if that page is in RAM or on the hard drive or really anywhere else. That's the memory manager's problem. It's the memory manager's job to resolve it. So let's say me, omar.exe, is a 64-bit process. And I say, hey, kernel, give me 1 megabyte of memory to work with. I need to, I don't know, do some math on this 1 megabyte of space. Kernel says, no problem. And it replies back and says, here, use address D1A746 followed by a whole bunch of zeros. Now, that address might sound like a random number that was generated. But the reality is that you can actually break up any address that you get back into a series of 9-bit indices followed by a 12-bit offset. Remember, this is for 64-bit architectures. So each of those indices is actually used in a series of tables that we call the page tables. So going back to the previous slide, we get those indexes, and then we plug them in at each step of the way here. And ultimately, we get to the last set of tables. And that contains a series of what we call page table entries. Page table entries are just 64-bit integers or data structures that tell the memory manager how to go about locating the actual page. Now, there's all sorts of different types of page table entries, or PTEs for short. For example, a hardware PTE tells the memory manager that your memory is actually in RAM. You're good to go. A software PTE tells you that you're out in the page file and you need to be fetched back from the hard drive. Then as you can see here, there's all sorts of other kinds of placeholder PTEs. Ultimately, they all help the memory manager resolve data. Okay, omar.exe made a request. I navigated through the page tables, and the PTE I ran into turned out to be a software PTE. Let's expand that data structure just a little bit here. So we see all these fields here, but the 2 fields that we're going to focus on today are pagefile low and pagefile high. Pagefile low is an index that's between 0 and 15, where each index corresponds to one of the page files on your disk. Pagefile index 0 is pagefile.sys. Pagefile index 1 is swapfile.sys. Pagefile high just tells you the offset you need to go to within that file to then retrieve your data. So let's look at a real-life example. This is in the Windows debugger, and I used the PTE extension on what was probably a random address. So we see the Windows debugger goes through, and it carves through the page tables for us. You can see that data on the left side. Then on the right side, we can actually see our PTE. Our PTE is a 64-bit data structure. In this case, it starts with 17A4D. And the Windows debugger has actually gone ahead and parsed some of it for us. We can see that it's in pagefile index 2, which we haven't really covered yet. We mentioned that pagefile index 0 is pagefile.sys, 1 is swapfile.sys, but what is 2? I don't know. We'll find out soon. And then there's pagefile high, which is the offset, 17A4D. So let's go ahead now and do a brief recap here. So I renamed omar.exe to notepad.exe. I want to go fetch my page. I have a virtual address, so I break apart that virtual address into a series of indices. I plug those index values into the page table, and I ultimately reach a PTE. Remember, the PTE is just a placeholder to to where my page actually resides. If it's a hardware PTE, I head down to RAM and I fetch it from there. Software PT, no problem. I go out to the hard drive. Ultimately, the PT is updated accordingly back to a hardware PT, and Notepad gets the page. Notepad has no idea that the memory manager just did all of this stuff under the hood. This is the model of paging that we call the demand paging model. So it's a pretty old model, and all sorts of updates, all sorts of performance optimizations have happened to it since like Windows 95. And really all of them revolve ultimately around the fact that getting a page back from the hard drive is an incredibly slow operation. Accessing your data from RAM is actually potentially orders of magnitude faster. So to leverage this fact, modern operating systems, Mac OS, Linux, Windows 10, Windows 8.1, they try to fit as much memory into RAM as possible, and they do that by compressing it. Compression has some pretty great upsides. For example, it's a highly parallelizable operation. That means that compression can utilize the 2, 4, 8, or 16 cores in our computers and perform work simultaneously. It's incredibly fast. And this actually allows us to have a flexible kernel that can be deployed in all sorts of locations. Who here knows that the same kernel deployed on Windows 10 enterprise servers is the same kernel that shows up in the Windows Phone? It's called the one kernel effort, and performance optimizations like this enable that possibility. So why don't we revisit our mystery page file again? I'm going to drive this in home again. Pagefile low index 0 is pagefile.sys. Index 1 is swapfile.sys. And we have to index 2, though, and the VM extension in the Windows debugger says, well, actually, I don't know anything about it. And it's like, OK, that's fantastic. So all this compressed data is actually stored in what we call a virtual store. More specifically, a RAM-backed virtual store. The store manager is a component of the kernel that creates all kinds of stores that ultimately support performance optimization. We may have heard of Superfetch, ReadyDrive, ReadyBoost. They're all technologies that ultimately are used to give the user a snappier experience. The idea is to move data away from slower storage and to leverage faster storage so the user doesn't have to wait on writes that go out to a hard drive. So on a default configured Windows build, we have one page file, one swap file. So index 2 ends up being the index that goes to our virtual store. Any page in the virtual store is going to be compressed using the express compression format. And after it's compressed, it's going to be stored in what we call a minimal process, or memcompression.exe. You won't find this process in the task manager, but if you have a kernel debugger set up, you can see it, and you might even be able to see it in Process Explorer. To be honest, I'm not sure. So if you want to see how much memory on your Windows 10 box is actually currently being compressed, head over to the task manager and check out the performance tab. You can get that information there. Now, to access data within the store manager, we need what we call a store manager page key. A store manager page key corresponds to a single page within the store manager's virtual store. Now, in the case of the RAM-backed store, we need two of our fields, pagefile low and pagefile high. We shift pagefile low left by 28 bits and then OR it with pagefile high to ultimately derive our SM page key. Now, that algorithm is subject to change and has changed a little bit in 1803 and 1809. If you're interested in that, you can check out the volatility source. It's very clearly defined there. Now, let's take a look at this example from our previous address we resolved. So we know pagefile low is 2, and pagefile high is 17A4D. If we follow that algorithm, we generate our key, 2001 7A4D. Really, we've effectively just smushed them together to get this key. Now, what do I actually do with this key? So this is where all the undocumented and ever-changing Windows 10 store manager structures come in. That store manager page key is ultimately used to derive metadata at each step along the way here. And that metadata is then used to reconstruct the address of our compressed page within the memcompression.exe process. So this is a pretty important point, so I'll just drive it in one more time. The store manager page key is used as we traverse these structures to extract metadata. That metadata then has some math operations performed on it, which ultimately helps us derive the address of our page within memcompression.exe. So, big picture. Okay, now I'm Notepad in Windows 10. I have an address from which I need to resolve a page, no problem. I go ahead, I walk through the page tables, and I ultimately end up at a PTE. Remember, the PTE is just a placeholder from which I can find my page. If it's a hardware PTE, I reach out to RAM. If it's a software PTE, I reach out to the hard drive. But in Windows 10 now, if it's a software PTE and it happens to be backed by a virtual store, I generate an SM page key, and then I traverse the undocumented structures using my SM page key sort of as a guide. Once I'm within the memcompression.exe process, the page can still lie within RAM, or it can be on the hard drive. Either way, the page is fetched, the PT is updated, Notepad gets the updated page. And believe it or not, this is way faster than reaching out to the hard drive to get your page. So that isn't so bad, right?
All right, thanks, Omar. No, not that bad at all, right? We got this. So one day, I'm closing out my malware ticket, and Omar chats me up, which was awesome. Told me about everything you just heard, and he wants to know, hey, can you integrate this into Volatility and Rekall? And I said, I don't know. So, if you're not familiar, Volatility and Rekall are two of the most popular open source memory forensics toolkits available. But neither of them can read these compressed pages. So what does that mean for us? Well, there's a lot of artifacts that we're just blind to. We can't see them. So I dove into Volatility, and I learned a lot about it. It has magic, it has layers, and it has plugins. So we'll start with plugins. So plugins are essentially commands you run with Volatility. And to do that from the command line, you first start off with Python. You tell it you want to run Volatility. You then give it your memory capture. You tell it, hey, this is a very specific type of Windows architecture and version that I'm using. And then you give it the plugin name and any artifacts. So when trying to integrate his research, I was like, hey, why don't we just create a plugin to do a proof of concept? So the plugin I wanted to create, I wanted to give it a virtual address of a known compressed page, and I wanted to get back the decompressed data. So I did just that. I created a plugin called Win10Deflate. It takes a process ID, in this case 3676, and it also takes a virtual address for a known compressed page. Here, hex 7C followed by 4 zeros. And we can see in the middle of the screen that I actually get back a hex dump of the decompressed data. Perfect. But this doesn't really scale, right? You need to know the virtual address ahead of time. So I had to figure out what could I do. And that's when I came across address spaces. So in Volatility, address spaces are like cake, which is why I put a cake on the screen. If you cut that cake, you get these nice layers. And here, each layer is an address space. And each layer deals with a very specific type of memory. And if you're wondering, the little strawberries are plugin. So they interfaces with all these layers. All right, so this stack of layers is responsible for translating virtual memory all the way down to physical memory. And it doesn't matter what the physical memory is. It could be a memory capture, a crash dump, hibernate file. The stack of address spaces will figure out how to do it and return you the data. So then I had an idea. Well, why don't we just create a new layer that deals with compressed pages? You know, find it, decompress it, and just return it. So that's what we did. So we're going to look at a plugin real quick called Volshell, which lets you change context into a process and just explore arbitrary memory. So previously, if you tried to read that address, 7C followed by 4 zeros, it's going to say, sorry, I don't know how to read that. But now with Flare's integration, you can read arbitrary memory, and if it lies in a compressed page, you can read it. Perfect. This is what I wanted. But to get here, we had to jump a few hurdles. And this is where we enter Volatility magic. I mean, I love this. Andrew Case, if you're out there, new logo submission. All right, so what is Volatility magic? Well, it's essentially an object that just encapsulates any type of global offset or magic number you're going to use throughout your code. So I use this. And the two offsets that we needed to make this happen was SM globals. So if you remember this slide from Omar's talk, SM globals is at the very bottom left. It's the very beginning of this whole chain to find the page in mem compression. So we need to find SM globals. And SM globals is publicly available in PDBs or a program database, but I can't ingest those with Volatility. So instead, we use a regular expression to scan over INTOS kernel memory and find it. Perfect. And in case you do know the address ahead of time, you can also specify it on the command line. All right, that's one address down. The other address we needed was the offset to paging file. So paging file points us to an array of these paging file addresses, which are the structures that represent the different page files. They tell us like the page file name, pagefile.sys, and now in Windows 10 there's also a Boolean value to let you know if it's a virtual store or not. So we tried to use a regular expression to find this, but the offset typically resided in a page that was either paged to disk or compressed. And since we can't read that compressed memory yet, not much we can do. So we decided to use the default value, index number 2. We can also specify it in the command line. All right, so that's our two offsets. So let's talk real quick about Rekall. So a member of our Flare team named Sebastian Vogel, he was the lead for integrating Omar's research into Rekall. Turns out Rekall can natively parse PDBs, so he easily got the offsets he needed. It's also pretty interesting. Rekall can actually ingest page files if you capture and supply them. So if data resided in a page paged out, he could read those too. So in the end, Sebastian created a new address space. Piece of cake. So what does this get us? It gets us what I'm going to call transparent translation, meaning all the current plugins and commands should just auto-magically be able to read this compressed data. So let's see some quick examples. Let's say you wanted to know all the different loaded drivers. You're going to run the modules command. Well, you might see a lot of empty spaces, right? That data lies in compressed pages and we can't read it. But now with Flare's integration, you should just be able to read that data as if it was never compressed in the first place. Let's say you wanted to know the different DLLs loaded in a process or its command line. Maybe there's a networking DLL loaded in Notepad that shouldn't be there. Well, previously, you just wouldn't be able to read that information. But now you can read it. And the last example I'm going to show is, let's say you needed hashes, like you're on an engagement and you wanted to dump the hashes from the system. Well, those typically are compressed. But now, with Flare's integration, you can read those. So let's all take a moment and just think of all the artifacts that could be just hiding there in those compressed pages that we're completely blinded to. Well, now we've unlocked those for you. All right, so that's cool, but let's see some real malware. So the malware we're going to go over is a sample that Omar reversed about 2 months ago. It starts off as an executable. It loads a DLL from the same directory. That DLL loads some shellcode. That shellcode reflectively loads a payload. And that payload loads more shellcode. That shellcode reflectively loads a server DLL, which is then responsible for all C2 communications for the payload. Oh, that's a mouthful. So a lot going on here. So Omar gives me this memory capture of a virtual machine that he actually infected with this malware. And he said, Blaine, go at it. So I used volatility as is, without any of our new research, and I wanted to see how far I could get in the IR process. So the first thing I did was run pstree, because I wanted to see the different processes running, and see if anything looked obviously suspicious. Nothing really looked obviously suspicious. The only thing that slightly stood out was this little process at the bottom, fmtoptions.exe. And the only thing that raised my eyebrow was it didn't have a parent. So it's a little orphan, which is fine, means the parent exited. But typically, processes have a parent tree leading back up to like explorer.exe. All right, so I decided to investigate fmtoptions.exe. So the next thing I did, I ran DLL list. I wanted to see the command line and if there's any other interesting DLLs. And there was one DLL of interest, fmtoptions.dll. It's running from the same directory, net_autocon. Okay, I'm doing pretty good. Then I wanted to run the handles command and look for different mutants or mutexes. Now these are typically good indicators of compromise. They're named objects. So here we see one, will staging _02, and another one, check and protect process thread. Okay, got some good indicators. Next, I wanted to see if there was any network connections. And there was actually one network connection from fmtoptions.exe. Okay, so I see some networking behavior. But that's where things started to fail. This was the fun part. So I tried to run malfind, which is a plugin looking for injected or reflectively loaded code. All the data was in compressed pages, so I didn't get any results. When I was looking for file handles, same result. And I was actually unable to dump the process or the DLL. This time, not because of compressed pages, but these pages were actually paged to disk, so I couldn't get those. And the last command I tried was vad dump, which just tries to look through different sections and dump those sections to disk for you. That didn't work either due to memory compression. So what are we going to do? I mean, we can go cry in a corner, but let's step back and do a quick overview. We're unable to actually carve out the executable or DLL, because those are paged to disk, and we've seen no evidence of the shellcode or the actual payloads. We've seen a little evidence of the C2 networking. But if you have to answer to a C-suite, right? Like, hey, did you find evil? And you're like, maybe? It's not going to be good. So now I wanted to rerun this whole process, but using Flare's integration to volatility. So I reran the handles command looking for mutexes, and actually found a new mutex, child 1634. Okay, new indicator I had previously missed. When I ran the handles command looking for files, I actually found all these file handles. And I actually found one to desktop/FMT options. So if I get the hard drive, now I have another place I can go look. And then my favorite plugin actually worked this time, malfind. It found 4 different sections, and all of these sections were marked page, execute, read, write, or an RWX section, which is pretty suspicious. And the 2 on the screen here, these are actually our shellcode. Perfect, I found our shellcode. The other 2 sections were actually more interesting to me. Both of these sections, not only were they read, write, execute, but they began with MZ. Everyone knows what this is, right? I hope so. It's a telltale sign of a Windows executable. So that means both of these are our payloads, right? Okay, so I found the evidence of these maliciousness. But now I actually want to extract this maliciousness. So I'm going to run the plugin called vad dump. And the vad is just a kernel structure that it does a lot of bookkeeping for Windows process memory, like how it's allocated, what its permissions are. So if you run this plugin, you can actually extract those to disk and then do some analysis using different third-party tools. So that's exactly what I did. So I picked one of the different payloads and I ran strings on it. And immediately, I'm like, hey, this looks just like the server DLL. And how did I know? Well, there's a string that literally says server DLL. There's also some other strings like HTTP send, HTTP receive, as well as some other IP addresses that are good indicators. Okay, so I found the server.dll, perfect. I ran strings on the other sample, and it turns out this was our actual malware payload. So on the far left, we can see some strings over here that to me stand out like sandbox evasion, or maybe anti-analysis, trying to check if it's running from maybe a directory called sample or virus, or maybe even named sample.exe. In the middle, I see a listing of different Windows versions. Malware will typically, as soon as it infects a system, do some type of quick triage or system survey just to figure out what type of machine it's infected, and might even send that information out to the command and control. So in the bottom right, we can actually see strings that correspond to our mutexes that we previously found. So now I have IOCs, but I'm pretty confident they're also malicious IOCs. And then my favorite string I found in here is in the top left, the Celaware.net1. All right, so we'll keep that in mind. So let's do a quick recap. I'm still unable to get the actual executable or DLL because it's paged to disk. But if I have the hard drive, I can go grab that, so that's fine. But now I've actually found evidence of all our payloads, and I've actually been able to extract them. So now if I get asked, hey, is there evil in this memory capture? I can say yes, and here is the evil. All right, so now that we've come this far, we're going to do some enhanced analysis. So you might want to really pay attention. It gets pretty technical. We're going to Google search our IOCs. So that's exactly what I did. I took this Celaware.net and I Google searched it. And the first result I got was a GitHub link to all these different YARA rules. So I followed that link and I found my string. And I also found at the top in the metadata a reference to a FireEye report for APT30. So now I'm going to go read this report, not duplicate all the effort reversing the sample, and call it a day. So how awesome was that, right? Beforehand, couldn't find it. Now, it's pretty obvious. So I guess to sum it up, Andrew Case once said, with Windows 10, you're not getting data you'd expect because it's compressed in memory. Well, now you can read that compressed memory. So, Andrew, I know Omar and I like beer, and we recently found the Roosevelt Room, which is awesome. Highly recommend it. So I think we should all go out and just grab a drink and talk about how awesome this is.
All right, thank you very much, Blaine. So once again, this was all brought to you by the Flare team, enabled this research to happen. For those of you interested in reverse engineering, we have the Flare On Challenge coming up. That'll be dropping at Black Hat. And speaking of Black Hat, we'll be giving a variant of this talk there, and we're going to focus in on the Windows 10 undocumented structures and then the challenges involved with tracking them down and reverse engineering them. So if you found this interesting, please join us there. Now for the good stuff. So all of this is available on GitHub now. So github.com/FireEye. And if you go to the Volatility repo, you'll find Blaine's work there. The Rekall repo will have Sebastian's work. And if you're interested in some of the other tools that we have Flare VM for malware analysis, and then Commando VM for red teaming work. All right, thank you very much. We appreciate it.
Thanks.